So hello everyone. I'm in a third year PhD thesis, and I will talk. And I will present you the preliminary results of a model with orthoparachemistry, and also the first results with an experiment since we an experiment on the nuclear spin conversion of H2 on the ices. So due to the poly-exclusion principle, when you have an hydrogenated or deuterated molecule, you have a nuclear spin isomer, and in the case of water, you have two isomers. So the ortho isomers when the two spins are in the parallel configuration, and the para isomer when the two spins are in the anti-parallel configuration. But why we are looking at the OPR in the ISM, it can be a parameter tracer such as the temperature of the medium, and we want to see its impact on the chemistry of the ISM. The OPR of water is widely studied in the ISM, and the values found are quite disparate. And in 2014, Choi found one of the lowest values reported in the ISM, and this values was found with a one-dimensional radiative transfer code, and the temperature is fixed in this code. So we need to find most accurate values. We need model with a maximum of physico-chemical processes such as the Meudon PDR code. So Pierre told us about the Meudon PDR code. So it's a one-dimensional model that computes the atomic and molecular structure of interstellar cloud, and it gives an analysis of physico-chemical processes. The model consists of a stationary plane parallel slab of gas and dust illuminated by a UV radiation field that coming from one or both sides of the cloud. And for each position in the cloud, the model computes the radiative transfer in the UV, the thermal balance by taking into account heating processes such as the photoelectric effect on dust, the chemistry in gas phase and the grain surfaces. So the model can be able to calculate for each position in the cloud the abundance of all the species. And for about 40 species, the excitation state is computed. And then the code can be able to calculate column densities of species. So why the study of H2 is so important for the interstellar medium? So H2 is the most abundant molecule in the interstellar medium, and for a given reaction, the reaction rate may be different depending on whether H2 is ortho or para. So the OPR of H2 can have a great impact on the chemistry. And when we are looking at the reactional chain leading to the water formation in the gas phase, we can see that we have H2 at almost each step of the reactional chain. So it can change the OPR of H2 in the interstellar medium. That's why we implemented an orthoparachemistry in the Meudon PDR code. And there is two processes that govern the orthoparachemistry in the Meudon PDR code. So the chemistry and the excitation. The chemistry for when you have a chemical equation with an isomer, an ortho isomer here with a reaction rate Q1, we modify the reaction rate by multiplying it with the population fraction of the isomer considered. So we modify the reaction rate depending on the orthoparach aspect of the species. And the excitation, we looked at different processes that populate and depopulate high level for a given species. So there is a few processes, the radiative processes, collisional processes, and the two that we are interested in for the orthopara ratio in the code is the formation and destruction processes, because we want to see if those two processes are dominant in the excitation when you have orthoparachemistry. This is a small example for H3 plus with the excitation. So the first equation creates H3 plus para, and the second equation creates destroys H3 plus para. And when you look the differential equation for H3 plus in the level, we modify the reaction rates with the population fraction of the two isomers here. And we weight the formation of H3 plus with Boltzmann distribution only on the para state. And for the destruction, we modify the reaction rate with the H3 plus para, and we have a function Z destruction that destroy H3 plus only on the para state. But it's important to notice that in the PDR code, the species XO and XP are not chemical species, and the excitation computation is only made for the X species. And then from this computation, we can finally deduce the population XO and XP. So we tested our model on the diffuse cloud with and without orthoparachemistry. So on the left, you have the two equations without orthoparachemistry, and the right, when you take into account the all configuration with the isomer, we have 7 equations for the first equation, and for the cosmic ray ionization, we have 2 equations. And the reaction rate is calculated by a modified Arrhenius law. And for this 7 equations, the selection rules are given in the OCAR's article, and the prescription for the cosmic ray ionization of H2 is that H2 ortho can only form H2 plus ortho, and H2 para can only form H2 plus para. And this is the results we found. So for the temperature, the excitation temperature of H2, we have exactly the same temperature with and without orthoparachemistry. And that is normal because we don't have in our model equation that form H2 with ortho and parachemistry. But when we look the excitation temperature of H2 plus, without orthoparachemistry, we have a temperature of 48 Kelvin. And with orthoparachemistry, we have a big decrease of the H2 plus excitation temperature to 26 Kelvin. And this temperature is in good agreement with the temperature observed in the ISM for a few diffuse cloud. More results are on the Le Bourlot and Tal article that coming very soon if you are interested in H2 plus temperature. For the experiment, we want to see the behavior of the nuclear spin isomers at the solid gas interface. So in cold region, H2 can stick to water ices, and we can measure the ortho to para ratio of H2 in a laboratory. And we want to see when the H2 is released in the gas phase, if we have a memory of this ortho to para ratio of H2 in the gas phase, comparing to the ortho to para ratio of H2 and ices. So several studies on the nuclear spin conversion of H2 have been carried out, and the results found are very different. So this is the 2 experiment that has been done at the LERMA. So with spaces, we found results, a characteristic time of conversion of 220 minutes, and for formalism, characteristic time of above 300 minutes, sorry. But our Japanese colleagues found much lower conversion time. So 8 minutes for Sujimoto and 52 minutes for Ueda. That's why we built a new experiment to repeat the measurement of the nuclear spin conversion of H2 on ices. So that's the new experimental setup. That's a neutral vacuum chamber that can reach a pressure of 3 to the minus 10 millibar. We have a cryostat that can reach a temperature of 6 Kelvin, and the dosing system here can produce controlled icy film on the substrate here, and we can coat H2 isotopologue on it. So when the ice is gross on the sample holder that can reach temperature to 6 to 300 Kelvin, we probe the ice by infrared spectroscopy to see the nuclear spin conversion. So the experiment consists of growing an ice of 1,000 layers of amorphous solid water on a substrate at 10 Kelvin. And the special deposition technique allows us to not destroying the background vacuum and to avoid redeposition during the duration of the experiment. On these ices, we're gonna saturate the surface with H2, and then we can probe the ice by infrared spectroscopy. So that's the first results obtained with COSPIN-U2 two weeks ago. So we can see the ortho and the para line of H2, and over time we have a decrease of the ortho line to the favor of the growth of the para line. So we have conversion of ortho molecule to para molecule. And when we look the positions of the line, we don't have the same for the gas phase and the solid phase. And it may be due to some interaction of H2 with the ices that can, it might be due to interaction with the ices. That's the fitting procedure to analyze the intensities. So we just need to improve to correct better the baseline. But we can see that the width of the ortho line is twice the width of the parallel. So that's the results of the experiment. So we can see the evolution of the ortho and para H2 molecule as a function of time. So the duration of the experiment is about 24 hours. So at the beginning, we have 75% of ortho molecule and 25% of para molecule. And we have a decrease of ortho molecule to the favor of the growth of para molecule. But what we can see here is at the end, we still have ortho molecule. So we should continue the experiment to see if at a given moment, all the ortho molecules are completely converted to para molecule. But we found a characteristic time of conversion of 390 minutes. And that's in the same order of magnitude that the two results obtained with the LARMA experiment. So to conclude, for the modelization part, we have a big decrease of the temperature of H2 plus with an orthopara chemistry, which is in good agreement with the observation. And the next step is to implement the oxygen chemistry to see the influence of H2 on the production of water. And to that, we're going to integrate the UGAN network, which is a gas phase chemical reaction network, which takes into account grain surface reaction and the orthopara aspect of the species. And the reactional chain for water production in gas phase is only 4 equation. But when we take the orthopara configuration, we have 16 configurations, so that can change a lot the ortho to para ratio of water. For the experiments, we saw that the nuclear spin conversion of H2 has been studied with different techniques. And the measure we made with SPICES, COSPIN-U2, and formalism give a characteristic time very close. But there is still a large discrepancy with the data collected in the literature. And we're going to do measurement with COSPIN-U2 on a large time scale to investigate the temporal dynamics. And also, we're going to investigate the temperature dependence of the nuclear spin conversion. We are still developing the COSPINU2 experiment to investigate the link between the OPR we measure in situ on the ice and the OPR when the molecules are released in the gas phase from the surface through thermal and non-thermal processes. So I would like to thank all these organizations for the fundings and also all the students with who we built the experiment, and especially Delphine at Toulouse with who I made the first experiment of the nuclear spin conversion. Thank you.